magnetic waves, class 12 physics. Okay, so we will continue from the last class. Since contradiction arise from our use of Ampere's circular law, this law must be missing something. The missing term must such that one gets the same magnetic field at point P, no matter what surface is used. And this is the figure. You can see these figures, and these are the figures, and we are talking about in these three figures. Okay. So next we will continue. Is there anything passing through the surface S between the plates of the capacitor? Yes, of course. The electric field, if the plate of the capacitor have an area A and a total charge Q, the magnitude of the electric field E between the plates Q upon A upon permittivity, the field is perpendicular to the surface of S, and it is given in figure 8.1 C. Okay. It has the same magnitude over the area A of the capacitor plates, and when I say outside it, so what is the electric flux? So the surface is using the Gauss law, okay, phi E mod E area 1 upon permittivity into charge upon A into A equal to A cancel and Q upon permittivity. Now if there charge Q on the capacitor plate changes with the time, there is a current I is equal to dq upon dt. So that using 8.3 this equation, so d phi e upon dt equal to d upon dt in bracket charge upon permittivity will equal to 1 upon permittivity into dq upon dt. This implies that for consistency, permittivity into charge upon sorry d phi q upon phi e upon dt into I, we can use I. So next one, this is the missing term and Ampere's circular law. If we generalize this law by adding to the total current carried by conductors through the surface another term which is permittivity times the rate of the change of electric flux through the same surface, the total has the same value of the current I for all surface. If this is done, there is no contradiction in the value of V obtained anywhere using the generalized Ampere's law. B at the point of P is non-zero no matter which surface is used for the calculating it. B at the point outside the plates in 8.1 in this figure. So next one, the current carried by the conductor due to the flow of the charge is called the conduction current. Once again, the current carried by the conductor due to the flow of the charge is called conduction current. Okay, the current given by 8 point in equation 8.4 in this equation, we can see that is the new term and is due to the changing electric field or electric displacement. Currents are Maxwell displacement current in figure 8.2. 8.2. Okay, so that the electric and magnetic field inside the parallel plate capacitor discussed above here. Okay, the next one, the generalization made by Maxwell then is following. The source of magnetic field is not just the conduction electric current due to charge, but also the time rate of the change of the electric field. More precisely, the total current I is the sum of the conduction current, okay, denoted by IC. Okay, and we are talking about these figures, and similarly, okay, the next one, and the displacement current denoted by ID equal to permittivity d phi upon d phi e upon dt. Okay, so we have I equal to IC plus ID will equal to IC plus permittivity into d phi e upon dt. This is the equation we can see, and we have to consider. The next one is, in explicit terms, this means that outside the capacitor plates, we have only conduction current IC is equal to I, and no displacement current I is equal to ID is equal to 0. As per example, ID is equal to 0. On the other hand, inside the capacitor, next one, there is a no conduction current IC is equal to 0, and there is only displacement current, so that ID is equal to I. Okay, the next one is, the generalized Ampere's crucial law has same from equation 8.1 we have seen in last page. With one difference, the total current passing through any surface of which the closed loop is the perimeter. This is the only English language class, not in bilingual. Sorry. The total current passing through any surface of which the closed loop is per perimeter is the sum of the conduction current and the displacement current. The generalized law is uh, integration B into di equal to mu 0 IC plus mu 0 permittivity d phi e upon dt. This is the equation, and which is known as the Ampere's Maxwell law. Okay, yes, only in English. In all respect, the displacement current has the same physical effect as the conduction current. In some cases, for example, study electric field in a conducting wire, the displacement currents may be zero, since the electric field E does not change with time. In other cases, for example, the charging capacitor above, both the conduction and displacement currents may be present in different regions of the space. In most of these cases, they both may be present in the same region of space, as there exists no perfectly conduction or perfectly insulating medium. Most interestingly, there may be a large region of space where there is no conduction current, but there is only displacement current due to the time varying electric field. In such a region, we expect a magnetic field, though there is no conduction current source. Thereby, the prediction of such a displacement current can be verified experimentally. For example, magnetic field, say a point M. Okay, in this figure, we are talking about, in this figure, say M. So next one, between the plates of the capacitor, okay, in this figure, and can be measured and is seen to be the same as the that just outside. Okay, so next one is the displacement current has literally for reaching consequences. One thing we immediately notice is that the laws of the electricity and magnetism are now more symmetrical. Faraday's law of conduction states that there is an induced EMF equal to rate of change of magnetic flux. Now, since the EMF between 2 points 1 and 2 is the work done per unit charge is taking from 1 to 2. The existence of EMF implies that existence induction by saying that the magnetic field changing with time gives rise to an electric field. Then the fact that an electric field changing with the time gives rise to magnetic field is the symmetrical counterpart that is a consequence of the displacement current being a source of magnetic field. Thus, time-dependent electric and magnetic field gives rise to each other. Faraday law of the electromagnetic induction and Ampere's Maxwell law give a quantitative expression of this statement, with with the current being the total current as in equation 8.5 we have seen here 8.5. Okay, the next one. One every important consequences of this symmetry is existence of the electromagnetic waves, which we have discussed in quantitatively in the next section. And this is the Maxwell's equations. You can see as well as much as possible. These are the very important equations. Thank you for watching. Okay, the next next subtopic, we will continue in few seconds. So thank you for watching.